Hi, it's Dr. Khan with 17.3 to 17.5. Here are the learning objectives for these sections. Today we're going to talk about rising air and how temperature can change as air rises due to actually the rising itself, the expanding or contracting of the air as it moves up or down in the atmosphere. We'll talk about why air rises and the concept of stability and instability. Adiabatic temperature changes are changes in temperature that are not associated with a change in heat energy. So strangely, there's a way to change temperature without either adding or subtracting heat. That's kind of a strange thing to think about, but actually when air is compressed or pushed together, it will heat. And when air expands, air particles are moving farther away from each other, the temperature will go down or cool. So these are temperature changes that are related to changes in the air pressure, not related to adding or subtracting heat. There are two rates at which we approximate how air is changing in temperature as it rises or sinks. And it really depends which rate you're going to use, depends on, is the air considered dry or is the air considered wet? So let's talk about what it means when it's saying dry air. Dry air just means that the air is not saturated. It's not reached its saturation point. So we talked about in the last lecture, if an air parcel, let's say a kilogram of air, can hold 10 grams of water, if it's only holding 7 grams of water, it's unsaturated. It's considered dry. If it's holding 9 grams of water and it can hold 10 grams of water, it's also considered dry. So dry just means it hasn't reached that point of saturation. So really there's only one amount of water vapor that it can hold where it'd be considered wet, and that would be when it's at the saturation point, when the temperature is at the dew point. So the dry adiabatic rate means that rising air is going to expand and cool, and for every 1,000 meters that we go up in the atmosphere, the temperature will drop by 10 degrees Celsius. So it's like a minus 10 degrees Celsius for every 1,000 meters that we go up. I also want to point out here, it's important to note our metric system, 1,000 meters is equal to 1 kilometer. And you'll find that useful, I believe, in your labs as well. Descending air that is coming down, is compressed and therefore warms or heats up. And that rate will be warming 10 degrees Celsius, so plus 10 degrees Celsius for every 1,000 meters or 1 kilometer. If our air is saturated, rising air will still cool and condense, but clouds will form. Why will clouds form? Because as air is saturated, if you're going to cool it even more, the air is going to be able to hold less water vapor. So as the air rises, it can't hold it. It has to put it down somewhere. It's going to form clouds. Now, we have to pause here to think about when water vapor turns into a liquid, these tiny little liquid droplets that become the clouds. Think about from 17.1, what is happening with heat energy as water vapor turns into liquid. So water vapor has a lot of energy and it has to give up or liberate or freeze some of that energy in order to turn into a liquid. Well, where does it give up its heat energy to? The water vapor becomes liquid and it's giving up its heat to the surrounding air. So this is what this bullet point means, it's liberating or freeing latent heat. As water vapor turns into the cloud droplets, we are actually heating up the atmosphere around it a little bit. So this heating up reduces the rate that the air is cooling as it rises. In other words, there's an offset that yes, air is rising and it's cooling. There's that adiabatic dry rate at which it's going to cool 10 degrees for every 1,000 meters. But because some heat is being released in the process of that air lifting, we're not getting as much of that cooling effect as we go up. So it's not going to be 10 degrees Celsius that we cool if we're at that wet adiabatic rate. The rate varies, but it's usually about, well, we were at 10 degrees for every 1,000 meters. It's about 5 degrees for every 1,000 meters due to relative humidity. So we're going to go with that wet adiabatic rate of 5 degrees Celsius. So notice the cooling rate is cut in half once we have wet air, because again, there's some of that heat offset from the liberated heat from the latent heat of condensation. So let's follow the life of a parcel or a bubble of air as it rises from the surface. So our story starts here at the ground. We have this surface air that's at 32 degrees Celsius, and it's warmer. Let's say it's less dense or warmer than the air that's around it, so it's going to rise. So as this air rises, we notice that it's not yet saturated. I know that because it's going to be rising at the dry rate until it hits this condensation level. And if we're unsure of where that condensation level is, we can just simply look in the sky and see, or measure up to the sky to see where clouds are forming. Sometimes this is really noticeable in the atmosphere, where you look up and you see that cloud bases are all at about the same level. So you'd look up at the sky and there's a bunch of clouds across the sky, but they all are kind of making a straight line in terms of where their bases start forming. That's the condensation level. That's the level at which the air had to rise, and that becomes saturated at that point, so that any lifting above and beyond that, we're going to have cloud formation. So again, we're going to start the life of the air down here at 32 degrees Celsius. We're going to go up 1,000 meters, which is the same thing as 1 kilometer. And that 1,000 meters, we're dropping down by 10 degrees Celsius, because that's the dry adiabatic rate. For every 1,000 meters, we're going to go down 10 degrees Celsius. And we'll go up another 1,000 meters. So we'll drop another 10 degrees, and then we'll do it again. Once we hit that 2 degrees Celsius, that must be our condensation level, our lifting condensation level, meaning that we've reached saturation point for this parcel of air, and condensation begins to take place. So now for the next 1,000 meters that we go up, instead of dropping by 10 degrees, we're only dropping by 5 degrees. Why? Well, we're dropping that 10 degrees, but remember, then some of that heat of condensation is being liberated, and it warms the air around it. So we don't get that full effect of dropping 10 degrees. It only drops 5 degrees between these 1,000 meters, and it only drops 5 degrees between 4,000 and 5,000 meters. Hopefully that makes sense to you. The rate just changes once we hit that saturation level. So what causes air to rise? There are 4 main processes that we'll look at. One is called orographic lifting, and this is when, let's say, for example, a mountain is in the way. So we have air that's, let's say, coming off of the Pacific Ocean and hitting the Sierra Nevada mountains, and it's forced to go upwards because it has nowhere else to go. So it's not like the air wanted to rise per se, it just has literally nowhere else to go. So elevated terrains, read that, mountains, right? Like mountains, places of higher elevation, act as barriers, so air is forced up and over the mountain. The result can be a rain shadow desert, because essentially we're going to squeeze out the moisture from that air as we force it up. So by the time it works its way down the other side of the mountain, we've wrung it out like a sponge, and it's now very dry air. The second type is frontal lifting. Cool air acts as a barrier to warm air, and the reason is colder air is more dense. So it's kind of like a plow coming through. Nothing is going to kind of make that big, dense pocket of air move. So when warm air moves in on cold air, or vice versa, warm air is going to be the one that's kind of bullied in the situation. It's a lot easier to lift up and over the cold air. So that's called frontal lifting. Fronts are part of storm systems, and we'll see one specifically that affects our weather a lot called mid-latitude cyclones. All right, so here is the image of orographic lifting. This, I think, is helpful to imagine that this is the Pacific Ocean, and these are, let's say, our Sierra Nevada mountains. Here we have wet air. Why is it wet? It's coming off the ocean. There's going to be a lot of moisture in this air, and it's being lifted up this Sierra Nevada range. When it is lifted up, it's going to reach its condensation point and start forming clouds and will precipitate. We'll have actually the water, the rain on this side, and notice that this side of the mountain is very green. It's receiving a lot of that rain. But by the time the air reaches the top of the range, we've really wrung it out, again, like a sponge, and it's incredibly dry air. Now, if we remember, we talked about lifting a bunch, but as air moves downward, it's going to compress and heat. So now we have hot, dry air, and that represents our Great Basin. That's why on the other side of the Sierra Nevada range, we have very dry conditions. So here on our windward side, the side where the wet air rises, we have very wet conditions. We'll have tree growth, right? A lot of green over here. And on the other side is called our leeward side. We have the rain shadow effect, meaning we're not going to get a lot of precipitation. We're going to get warm, dry air. Frontal lifting, again, cold air, think about it as like dense and unmoving and kind of like a plow, where our warm air is much less dense and will be forced up and over the cold air. Well, when we force warm air up, it's going to eventually reach its condensation level. If it continues to keep rising above this cold air, it'll form precipitation. And sometimes this is how we get our very vertically developing clouds, like our thunder clouds, our thunderstorms that we have severe storms or maybe even tornadoes from, come from this quick lifting, this almost straight vertical lifting of our warm air upwards, forcing it to condense. Our next two processes include convergence, so air coming together or meeting together. This happens in areas of low pressure. We'll see in the next chapter here that air will flow from an area of high pressure to an area of low pressure. So just like a low point on a map, if we think about low point in a terrain, that's where all the water is going to flow to. If we have a big rainstorm, you have your low places, your low points, and all the water kind of converges there. We can think about a low pressure as the same thing. On a map, if we have a low pressure system that's developing over our area, the air is all going to be flowing inward together. And that air is going to pile up, and it's not going to have anywhere to go except up. So that rising air is something that we see with convergence. And then something called localized convective lifting. So we might have one piece of the surface of the ground, let's say, a blacktop playground, let's say a big blacktop playground at a school. So that's going to be this blacktop area is going to be heated more strongly than lighter colored surfaces. You might have noticed that, like a dark colored surface will heat up a lot more in the sun. So what you're going to have is a heating that's not equally distributed across a surface. And when one area is heated more than another, remember, heating causes air to expand, and that's going to make it less dense. And if a pocket or bubble of air is less dense than the air around it, it's going to rise. All right, so first we have this convergence idea. There's a smart figure that you can watch here, and this gives us an idea actually of why Florida has rain showers pretty much regularly in the afternoon. We have winds that are converging from the Atlantic and the Gulf of Mexico, coming together and lifting to create these thunderstorms that often only last a few minutes and then are over. Or we have this darker patch of ground that's being heated more strongly than the ground around it. So it causes this bubble or pocket of air to lift, and you'll get a nice puffy little kind of cumulus cloud here. So you might have seen that. You go outside and there's a whole bunch of these little kind of beautiful floating clouds that are puffy looking on a summer day, and it's not raining. There's just these puffy clouds in the sky. That's what this is formed from, this localized convective lifting from pockets that were more strongly heated than the air around it. Atmospheric stability, there's a lot here, and this often is a concept that confuses students, but I'm going to make it very easy for you to understand, I'm hoping, and thinking about what does it mean if it's stable air or if the air is not stable. So stable air means that it's not going to rise. Remember, rising is what is going to cause cloud formation and possibly even storms. So, stable air isn't going to be rising if it's not going anywhere. So, this is what it's talking about when it says resists. So, it doesn't want to. It resists vertical displacement. In other words, it resists going up. Why does it resist going up? Well, maybe that's cooler than the surrounding air. Remember, if it's cooler than the air around it, it's going to be more dense, so it's not going to rise. It's more dense. Or it just is more dense than the surrounding air. Or if the air wants to sink. And usually that's really all typically associated with density. And air is considered stable. When air is considered stable, there's no cooling because it's not rising. All right, we're going to skip this next concept here. The book talks a lot about this environmental lapse rate compared to the wet adiabatic rate. We're going to skip over that because what I really want you to understand is simply air that's stable will not rise, period. If you have air that's not stable, so instability, you have rising air that's going to keep rising. And that's really the extent of what I need you to understand about air that's not stable. So it's rising. It's rising either because it's warmer than the surrounding air, meaning it's less dense than the surrounding air, and it's going to continue to keep rising until it gets to a point where it's the same temperature as the air around it. And that's where we have this instability, is when we have cloud formation and possibly even cloud formation that leads to things like storms. Again, don't worry about conditional instability. If you understand those two concepts that I just referred to in terms of what does it mean to be stable, it's not rising. What does it mean if it's not stable or unstable, it's going to keep rising. And that is it for 17.3 to 17.